In the previous video, we had a look at the mathematical aspect of what happens when an AC source is connected to a capacitor. So here I have the capacitor and here I have the AC source. And in this particular video, let us have a look at the intuitive side of all those mathematical equations and everything we derived in the previous video. So to begin with, this is the equation that gives us the voltage at any instant in time, and we know that the voltage at any instant in time equals the peak voltage times sine omega t, and that is our AC voltage. And it is always a good idea to draw a graph of things that change. So here let us quickly draw a graph. So let us start by plotting the voltage, and because it is a sine curve, see, sine omega t, so the voltage varies just like a sine curve, and it starts at 0, goes to a maximum positive value, and then it starts reducing, comes to 0, then goes to a negative maximum value, and then comes back to 0, and this continues, right? So let us just stick to one particular wave, one particular oscillation, one particular cycle of voltage, the voltage change. And now let us have a look at what happens at the capacitor. The first thing to keep in mind is that the source voltage is always equal to the potential difference across the plates because of Kirchhoff's law. So this is the only place where the electrons drop their potential, and the drop in potential is equal to the potential difference between the two plates, and so that potential difference should be equal to the potential gained at the source, or the source potential. So this here is the graph of the source potential, but we know that this should also equal the potential difference across the plates. So this is also the graph of the potential difference across the two plates of the capacitor, right? Now at this point here, the potential difference across the two plates is 0, right? We can see that it's the graph is at 0, so the potential difference is 0, and that simply indicates that at this particular moment the capacitor is completely empty. It has no charge, because it is the charge that creates the electric field and the potential difference, and the that potential difference, and because that potential difference is 0 at this point, there should be no charge on the either of the plates, and so the capacitor is completely discharged or completely uncharged, either way. And so the charge at this point, so I'll also draw the charge side by side. I'll use a dotted line to represent the charge. So charge at this point is also 0. Now as the potential difference increases across the two plates, we know that the potential difference, so I'll write the equation. Capacitance equals Q by V, and I can simply shift the V on that side and bring the C on this side. So V equals Q by C, and C is the constant, so ignore that for now. But we can see that the voltage is directly proportional to the charge, or we can say it the other way too. The charge on the plates is directly proportional to the potential difference between the two plates. So as the potential difference increases, the charge on the two plates also increases proportionately. The trend, the rate at which, the way in which the charge increases is similar to the potential difference across the two plates, or the source voltage. And obviously the magnitude or the maximum amplitude can vary, because we cannot compare the charge to voltage. Voltage is in volts and charge is in coulombs, so we cannot really compare them directly, but yeah, their amplitude is just independent. Comparing the amplitude of the two waves, the two quantities, just doesn't make any sense. So I'm just making a random amplitude, don't focus on that, but yeah, the trend matters here. So the voltage, as the voltage increases, the charge also on the plates also increases till this point, and at this point the plates are completely charged. They are charged to their maximum limit that they would be charged, and at this point we have some charge, we have some charge Q on both the plates. And yeah, after this moment, gradually the potential difference between the two plates begins to decrease, because the source voltage begins to decrease, and so we can conclude that as the potential difference is decreasing, the charge on the two plates must also be decreasing, and it continues to decrease, and again when the potential difference between the two plates is 0, the charge on the two plates must also be 0, and the same thing continues as the polarity switches, as the potential difference switches, and it gains a negative value. negative value, negative potential difference simply means that the polarity has changed this time, but the rest of it remains the same. So now we would get some charge stored, some charge would again get stored, but this time, you know, on the opposite plate. So let's say on the first charging, say, so I'll also plot this part. In this section here we get some charging, so I'll just write that charging. And you know, in the second section, in this section we get discharge. So in this section the capacitor is discharging, in this section it is charging, in this section it is discharging, and again in this section here it would charge, it would gain charge, just the polarity would be switched, and then again in this section it would get discharged because the potential difference also reducing, getting back to 0, and so in this section it would discharge. I'll use the C for charge and D for discharge, and I hope that all fits. And just to make a bit of space, I think I should just shift all this downwards because I now need to fit in the current also. So yeah, in this section I get charging, in this section I get discharging, D discharging, C charging, right? Now comes the turn for the main character, which is the current. I think I should switch the color for that. I'll take black for current, black current. So current is nothing but the rate at which charge is flowing through the circuit, right? It's the rate of change of rate at which charge is flowing through the circuit, and that rate at which the rate at which charge is flowing through the circuit is equal to the rate at which charge is increasing or getting deposited at the plates, or also at the rate at which, in some other case, the rate at which charge is maybe getting discharged from the plates. Either way, it depends on this situation, but yeah, I hope you get the idea. Charge is nothing but the rate at which charge, current is nothing but the rate at which charge is flowing, right? So current must be nothing but the derivative of charge, or rather the slope of the charge curve, right, which is the dotted line here. So at this starting moment we see that the charge increases quite rapidly, right, and obviously it is increasing, so it has a positive slope. So the slope is, you know, this way, it is increasing, so it has a positive slope, and it has the maximum value right now, the slope. So because the slope has a maximum value, the current must have a maximum value. So let's say this is the maximum value of the current, and after that the slope, you know, it gradually decreases as you go upwards, and at this particular peak the slope becomes 0. So at this instant in time the slope is 0, which means the current must be 0. So current at this point in time is 0, at this level 0. So the current goes from this maximum value to, you know, okay, I should do a solid line to represent current, and it goes down to 0 till this point. So the current is slowly reducing. After this, so at this point the capacitor is completely charged up, and after this the capacitor begins to discharge, and to discharge it, the current runs in the opposite direction. So now the current switches its direction, it flows in the negative direction, so to speak. You have negative current, and you can see the slope begins to, you know, it begins to increase in magnitude, but obviously the slope is negative, so the current must be negative, but the current should increase in magnitude, and the slope increases to this point. At this point it attains its maximum value, the slope. So at this instant in time the current must have a maximum value, let's say the maximum value of this much, and so it increases gradually and reaches its maximum value just like that. And after this again you can see that the charge, now after the charge has reached 0, it keeps on, now the capacitor, at this point the capacitor is completely discharged. Now it begins to charge in the opposite direction, in the opposite, you know, polarity, and so the current must flow in the opposite direction. So now the current, I mean, it should flow in the same direction, but so in the same direction as it was discharging. So let's say you have positive charge stored on this side, so the current flows in that direction to make the positive charge discharge, and then it should flow in the same direction to make the capacitor charge in the opposite direction, right? I hope you can visualize that part. So now the current, and obviously we can see that the slope now begins to reduce and reach 0 till here. So at this point the slope is 0, so the current must be 0 at this point. So the current must slowly drop, or rather, you know, yeah, it should drop and reach 0 till this point. And after this, so at this point here, in this particular instant in time, the capacitor has been completely charged in the opposite direction with an opposite polarity. And at this point, you can see that the charge has a maximum value and the current is 0 because it is completely charged. You don't need any current flow now, right? And after this, now the capacitor has to discharge, so the current switches its direction from negative to positive, and the slope, you can see, begins to slowly increase. So the current must slowly increase, and it slowly increases. At this point, the charge curve has a maximum slope, so the current should have a maximum value, and yeah, it just increases like that, just like that. And that, there you go, you have your current graph. And now I hope it makes a little bit more intuitive sense. And you can see that the voltage graph and the current graph are not in phase. What do I mean by them not being in phase? It simply means that the current graph and the voltage graph reach their peak at different instants in time. And you can see that actually the current or rather the voltage lags the current graph by 1/4 cycle. And what do I mean by that? Well, you can see that the current graph reaches its peak at this moment in time, but you have to wait for some time. You have to wait for this much time, and after this much time has passed, now the voltage graph reaches its peak. So the voltage graph is actually lagging behind. And lagging behind how much? Well, this is a complete cycle, or rather a complete oscillation or complete wave, a complete cycle. This much is a half cycle, and this much is a 1/4. This much is 1/4 cycle. And you can see that this much is the phase difference between the current, which reaches its peak here, and the voltage, which reaches its peak here. So this is the difference between the two quantities, and so this is called the phase difference between the two, and both of them have a phase difference of 1/4 cycle, which is also called a phase difference of pi/2. And that is why when we write the equation for current, I don't have space to write that. Well, I'll just fit that in here. Current equals peak current times sine. Do I have space? Yeah, I have space. Omega t plus pi by 2. I hope that fits. Yeah, that fits. So this pi/2 here, omega t plus pi/2, actually represents this phase difference. It simply tells us that this current is actually pi/2 or pi/2. Pi/2 is 90. 90 is 1/4 cycle, 1/4 of the circle. So it simply means that it is 1/4 cycle ahead of the voltage. And yeah, don't get confused by this pi/4 and the connection between pi/4 and 1/4 cycle and why is it lagging. I mean, all that we will get into more detail about all that when we do phasors and all that. But for now, I hope you are getting the intuitive idea of what is happening at the exact root level when we talk about how the current increases or how the charge increases, or all that thing. And yeah, I hope you get a better understanding of what all those equations mean and how charge and current and everything are connected and working in this particular arrangement. That's it for this video.